Hi, my name is Jack Reinhardt, and today I am going to be talking about the Navier Stokes equations, their development, mathematical basis, solutions, and applications. So, just as an introduction, the Navier Stokes equations are a heavily used set of nonlinear partial differential equations that model the flow of fluids through many different regimes and geometries. They are also take into account the viscosity and inertia of the fluid, which is something that earlier fluid flow models neglected, which caused many discrepancies between those models and reality. The Navier-Stokes equations have applications across many scientific and engineering disciplines, from fluid flow through a pump to air flowing around a rocket nozzle, and they have had a major impact on society since they were developed. The Navier-Stokes equations were developed in the early 1800s. The equations were derived independently by George Gabriel Stokes and Claude Louis Navier. These equations were a generalization of the Euler equations for fluid dynamics, which were published by Leonhard Euler in 1757. As an interesting side note, the Euler equations can be derived from the Navier-Stokes equations by assuming that the fluid has no viscosity and no thermal conductivity. The Navier-Stokes equations use Euler's equations as well as Newton's laws of motion to develop a set of equations that take into account the viscosity of the working fluid, which was a major step forward for the field of fluid dynamics. However, it is extremely difficult to get practical analytical solutions from the resulting set of nonlinear partial differential equations, so the Navier-Stokes equations didn't truly begin to shine until computers came into their own in the late 1960s, and it was possible to solve the Navier-Stokes equations numerically. Despite the focus on numerical solutions, analytical solutions to the equations do exist. However, they are prone to extreme instability. There are a number of mathematical concepts and assumptions that went into the development of the Navier-Stokes equations. The basic assumptions in the derivation are that mass, momentum, and energy are all conserved. Conservation equations are developed for each of these quantities and are used in the development of the Navier-Stokes equations. It is also assumed that the working fluid is a continuum rather than a set of discrete particles, and that all fields of interest, including pressure, flow velocity, density, and temperature, are all at least weakly differentiable. It is also sometimes necessary to consider a finite control volume over which these principles are applied. The derivation of the Navier-Stokes equations involves many different mathematics and physics concepts. Some of these concepts are the Reynolds transport theorem, the divergence theorem, and the Leibniz rule, which are all used in the development of the conservation law for an intensive property. The derivation of these equations also involves the use of Newton's laws of motion, the material derivative, the chain rule, gradients, and stress tensors, all of which results in a system of nonlinear partial differential equations that, as previously discussed, are very difficult to solve analytically. Due to the issues with the analytical solutions, the Navier-Stokes equations are often discretized through a number of different methods, such as finite differencing, that allow for numerical approximations of specific applications of these equations for certain geometries and settings. The general form of the Navier-Stokes equations need to be narrowed down using assumptions and limiting conditions in order for them to be useful. This is done by applying the conditions to the appropriate terms of the equation and simplifying. There are several types of assumption that influence the structure of the equations. Some of these conditions are whether or not you are considering a Newtonian versus a non-Newtonian fluid, compressible or incompressible fluid, or even viscous versus non-viscous flow. All of these conditions depend on the working fluid and influence the structure of the final set of equations. One common form of the Navier-Stokes equations is shown on the screen, and as you can see, it consists of terms for velocity, density, pressure, viscosity, and externally applied forces such as gravity. This form of the equations is for an incompressible Newtonian fluid, and the form of these equations can change quite a bit if the assumptions used in the derivation are changed. As previously discussed, there are many real-world applications of the Navier Stokes equations across many different scientific and engineering fields. Some of these applications are listed, such as plane and boat design, weather forecasting, motor and pump design, pollution modeling, and many more, all of which can be modeled through the Navier Stokes equations. In fact, the Navier Stokes equations are applicable for essentially any situation where the inertia and viscosity of the fluid plays a role. The Navier Stokes equations can even be extended into the turbulent regions of fluid flow, which is extremely important when examining, for example, the heat transfer between a fluid and a surface. The fluid regime, turbulent versus laminar, greatly impacts the heat transfer rate, and while there are approximations to model the effects of this phenomena, this may be insufficient for high-performance applications, which makes the possibility of modeling turbulent flow with a high degree of accuracy very important. Turbulent flow can also cause cavitation, which can degrade materials, and there are many more examples of the usefulness of the Navier Stokes equations. The main way that the Navier Stokes equations are applied to modeling and design problems is through computational fluid dynamics simulations. These simulations are done by discretizing the Navier Stokes equations through different methods, each based on the situation being modeled in the simulation. Some of these methods include the finite differencing method and the conservation form. This discretized form of the Navier Stokes equation is then used to calculate an approximate solution to the equations. This can be done to a high degree of accuracy, even for some complex fluid flow problems. In recent years, as computers have gotten more powerful, commercial computational fluid dynamics programs have started to become available, even to people not highly versed in the field or without access to high-performance computers. In fact, I was personally able to use the program Star CCM Plus to model an engineering design that I was developing as part of my engineering curriculum. And I suspect that as technology continues to develop, these programs will become even more useful and user-friendly. In conclusion, the Navier Stokes equations are an extremely powerful set of nonlinear partial differential equations that have many useful real-world applications. They have helped develop and model across many fields of science and engineering. The main way that these equations are used is through discretization and numerical approximation of the equations. However, these equations remain an active topic of research in mathematics. In fact, the Navier Stokes equation is one of the millennium problems, and there is $1 million reward for a general solution to these equations, which just goes to show how much of an impact these fluid flow equations have on both society and technology.